In this video, you will learn how to solve some problems on internal energy. A system evolves 50 joules of heat, but 75 joules of work is done on the system. Find the internal or the change in internal energy. Now let's analyze the problem here first. It says a system evolves heat. So when it evolves heat, when the system evolves heat, that means the internal energy decreases. And when work done on the system, then the internal energy increases. Now let's identify the given in the problem. So we're given here 50 joules of heat and 75 joules of work. Now how do we solve for the change in internal energy? So the change in internal energy is just equal to the heat minus the work. Now, what we're going to do next is we just plug in the given values of heat and work. But we have to take note the sign of each of them. So it says here system evolves 50 joules of heat. So that means it is negative because when the system evolves heat, the internal energy decreases. Therefore, the heat should be negative. So negative 50 joules minus, it says here, and take note that system evolves heat also means the heat flows from the system to the surrounding. That means it is exothermic. That's why the amount of heat here is negative. And for the work is done on the system, it is also negative. So this would become minus negative 75 joules. So the change in internal energy is just equal to negative 50 joules plus 75 joules, which is just positive 25 joules. So this is the answer here. How about we're given this problem here? A system gains 35 joules of heat, but it also does 65 joules of work. Find the change in internal energy. So let's analyze the problem first. It says here the system gains heat. So that means it absorbs heat. So when it absorbs heat, the internal energy of the system increases. And it also says here that the system does the work. So that means the internal energy of the system decreases. So does the work, system does the work, then the internal energy decreases. And now let's identify the given in the problem. So we're given here the heat gained by the system, which is 35 joules, and then the system does work, which is 65 joules. Then using the formula in finding the internal energy or the change in internal energy given the heat and work, so it's just delta E, or the change in internal energy. In some cases we use U as internal energy, equals the heat minus the work. Alright, so in this case it says the system gains amount of heat or absorbs heat, so that means it's positive. So this is positive 35 joules minus the system does the work, so this is also positive 65 joules. Therefore, the change in internal energy is just equal to 35 minus 65, or just minus 30 joules. How about this problem here? The heat of combustion at constant volume of CH4 or methane gas is measured in a bomb calorimeter at 25 degrees Celsius and is found to be negative 885.4 kilojoules per mole. What is delta H? Or the heat of reaction. Now the first thing we do here is to write a balanced chemical equation for the complete combustion of methane. Because it says here the heat of combustion. So that would be CH4 gas plus oxygen, then CO2 gas. Okay, all of these are gases. And then water. Okay. So we need to balance this. So we have how many oxygen here? It should be 2 here because there are 2 oxygens here. 4. Okay, I think that one is already balanced. So methane here, CH4 is methane. It reacts with oxygen gas from the air, and then it produces carbon dioxide and water vapor. Alright, so we have already written the balanced chemical equation or reaction of the heat of combustion of methane gas. Now let's solve for the heat, change in heat. And we're given here the internal energy. Alright, so we use the formula delta E equals the change in heat minus the pressure, in this case internal pressure, delta V, or the change in volume. It says here that the volume is constant and PV is just equal to nRT, or P delta V is just equal to, okay, nRT, P delta V, change in volume, is equal to the change in the number of moles of the gases times the gas constant R plus times the temperature. And the given temperature here is 25 degrees Celsius. Alright, so we're given the internal energy. We have, alright, so we have P delta V, which is just the change in the number of moles involved in the reaction. So that would be the number of moles of the products minus the number of moles of the reactants. And then the ideal gas constant and the temperature. So let's solve for delta N, okay, of the gases. So that means the number of moles of water is not included since it is liquid. So the number of moles of the product, in this case is carbon dioxide and it has only 1 mole, then minus the total number of moles of the reactants, which is 3. So this is just equal to negative 2. And now we can plug in all the given values. So to solve for the change in heat here, delta H, this is just equal to delta E plus P delta V. Okay, it should be internal. Or delta E plus delta N RT. Right, and this is just equal to negative 885.4 kilojoules per mole plus, okay, there's no more space, so I have to delete this one. Okay. So delta H is just equal to delta E, which is negative 885.4 kilojoules per mole. Right. And that is plus delta Ng, number of moles, the change in number of moles, which is negative 2 times the ideal gas constant R, which is 8.314 joules per Kelvin mole. So we use Kelvin here, so that means we need to convert 25 degrees Celsius to Kelvin, and that is 298 Kelvin. You just have to add 273 Kelvin there. So this is times 298 Kelvin. And notice here that the unit of the ideal gas constant is in joules per Kelvin mole. So we need to multiply this by 1 kilojoule per 1000 joules. So joules here cancel out, and then the unit will be in kilojoules per mole. The Kelvin unit also cancels out. So delta H is just equal to negative 885.4 plus negative 2 times, what's this, 8.314 over 1000 times 298, and the unit will be kilojoules per mole. So calculating that, this would give us negative 890.4 kilojoules per mole. So that is the amount of heat.